In this video, we're going to be looking at evaluating line integrals of scalar fields. So a scalar field refers to the case where we're assigning a scalar value to every point in some region. That means that only a magnitude is shown because there's no direction that's going to be associated with those points. So for example, we can take a look at R2. And in that case, we'll know we're dealing with a scalar field when we see something like this, f of x and y. As you can see here, if we put in some values x and y, we're going to get an output that's a scalar. There's not going to be any direction that comes out from this function. Similarly, we can look at R3, and it's essentially the same thing, but we're just going to introduce another variable here, so x, y, and z. And so in those two cases, we can easily tell a scalar field from a vector field, which is another class that we can look at. Now, again, just to make the point very clear, what makes these two cases a scalar field is that the output is always going to be a scalar value. Now, in this video, we're going to be looking at the two different types of line integrals that we might see with scalar fields. So there are two types. Now the first one has to do when we take the line integral with respect to a coordinate. Now when we talk about a coordinate here, we're referring to the variables x and y, for example. Now in all the examples we'll do in this video, or all the cases we'll talk about, we're going to be looking at R2, but the process is very similar for R3 as well. Now when we're referring to a coordinate, we would see something, for example, like this. The line integral of some function f of x and y, but then the coordinate part means that we're going to take that integral with respect to x, for example, or we might see something like this, again the same function, whatever that might be, but then we'll have dy here. And so when we talk about a coordinate, we're referring to this dx or this dy. We're integrating with respect to that coordinate. Now the alternative to this situation is if we look at an arc length, the arc length. So this doesn't necessarily depend on a specific coordinate. We can do any kind of curve. So we would see this. So again, the same line integral, f of x, y, but here we would usually see this denoted as ds. So again, the differential part here is what tells us we're looking at an arc length compared to just a coordinate. However, even though we made the distinction here, you can think of dx and dy as just being an arc length too, but the only difference is all the other components are just going to be 0. So for example, dx could also be an arc length, but we're only looking at the x direction, with the other values just being 0. So in that case, these two types are not really all that different. It's just mostly about what we're talking about. Are we looking at dx and dy, or are we looking at ds? Now for the c portion of the line integral, which of course is very important when we're trying to complete this integral, it doesn't matter if we're talking about a coordinate or an arc length. We still need to make sure that we're talking about c parametrically. And what that means is we want to look at c in terms of a vector function. So we want to illustrate c parametrically. So that would look something like this. We have the curve c that we might be given in the question, and we want to write it as some vector function here. In this case, I'll just denote it with an r. We're going to choose the parameter t, and now we want to write it like this, where we have two functions, x of t and y of t. And of course, we want to talk about this on some interval a and b. So I'll just explain this quickly so you can kind of make sense of what's going on here. Usually we might be given c in just a normal equation where y is equal to some function of x or some combination like that. But what we want to do here is we want to introduce a common parameter t and rewrite all the x values and all the y values that correspond to each other with a function of t. This might seem a bit complicated right now, but when we do some examples, it will be a lot more clear about what we're talking about. The other part to keep in mind is this a and b that we're talking about. This is referring to the bounds on C, because obviously when we're looking at a line integral, it makes a lot of sense if we're looking at it bounded. We want just to look at a specific section. And again, when we do some examples, that will make a lot of sense as well. Now, once we have all of this, it's actually quite simple. What the goal is we want to convert a line integral to a definite integral. So we want to move from a line integral, which is what we'll start with, and we want that to be a definite integral. And the reason we're doing this is because we don't really know how to compute a line integral as it is, but a definite integral is much easier to compute. So the idea here is that for each part of a line integral, we want to transform it or substitute different parts into it to create it or to transform it into a definite integral. Now, there are several ways for us to illustrate C parametrically, as I mentioned up here. And we're going to need to use how we describe C in order to substitute values into our line integral to make it a definite integral. The important point to note here is that my x of t might be different from yours, for example, or our y of t's might be different because there's a lot of ways for us to illustrate C parametrically. But the end result, the line integral, doesn't actually change. The only thing to make sure is that whatever values of x and t and y of t you're using, it needs to give the correct orientation of C. And when we do some examples, you'll see what that means. But that's just something to keep in mind. So going back to this table that we'll make here, there's a lot of different things we might see in a line integral from a question. So there might be some x's, there could be y's, we might see a dx, we might see a dy, and obviously the last one is the ds. Now, if we leave it just like that, we don't really know how to compute a line integral. But now we can substitute values in to correspond to these components. So if we see an x in the line integral, we'll replace it with x of t. If we see a y, we'll replace it with y of t. And just to remind you, the x of t and the y of t are referring to C, which we describe parametrically up here. If we see a dx, we want to write it as x prime of t dt. Now this might seem a little bit confusing what we're doing here, but I'll show you in a second why it makes a lot of sense. Similarly for dy, we're going to say y prime of t dt. And so why does this make sense? Well, let's consider this. If I just gave you dx dt, we know that that's essentially meaning some function x, we're taking the derivative of it with respect to t. Now, with just some simple rearrangements, I could therefore say that dx should probably be equal to x prime of t dt, which is essentially what we're saying here, and then we can just repeat that with a function y instead. And so this allows us to transform a dx into a dt. Finally, for the arc length part of it, here we're not just talking about an arc length, but we're trying to integrate with respect to the arc length. So it looks slightly different from just a normal arc length. So we have x prime of t squared. We add to it the derivative of y of t, and we square that as well. And then we want to square root this entire thing. And of course, we'll also include the dt. Now, you can memorize this chart, but if you understand what's going on here, it makes a lot of sense. The reason we don't want dx, dy, or ds is because the whole idea here is we're trying to move from a line integral that would have x's and y's, and we want just a definite integral of only one variable t, because x of t is some function of t, y of t again is a function of just t. If we left dx or dy or ds, it wouldn't really make a lot of sense because we don't have those variables really anymore. We're talking about t. So we want to convert it into dt. So we're trying to substitute these values in place. Now, the thing to keep in mind here is that some problems might involve more than one differential. So for example, we might have a question where there's a lot of different parts of the function going on, and we might have dx and dy. And that might be confusing at first, but we'll see in a later example that it's not actually that bad. Even if we have combinations of it, just remember to take it piece by piece and substitute the right parts into it. Now I just want to go over an example of how this might look quickly. So let's say we have the line integral of some function f here. We're going to have the variable x that's given in that function, and we're also going to have the variable y, and let's just say we want to integrate this with respect to dx, for example. So this could be any function f, whatever it might be. Let's say we started with this. Now we want to create this into a definite integral. So we're going to change it to the bounds a and b. I'll talk a little bit in a second about what this a and b is referring to and why it's very important. But let's just go on to the function part of it. So again, we're still going to have the same function f, but the difference here is that instead of just x, the normal x, we want to replace it with x of t. And instead of just the normal y, we want to replace it with y of t, which again, as a reminder, is coming from how we are describing c parametrically. So going back here, the last part we need to talk about is the dx. Again, like I mentioned earlier, if we just left it dx, it wouldn't really make a lot of sense. We want to integrate with respect to t. So to do that, we can just write here x prime of t dt. Now going back to the a and b bounds, this is what I was mentioning up here, where we're talking about c parametrically. We want to describe c using x of t and y of t on some interval a and b. What's important to note is when we talk about a and b, we are referring to the variable t. In a question, they might give you a point, maybe x comma y, or they might just give you the x bounds or the y bounds. Whatever that might be, we need to make sure that we are rewriting it in terms of t. This is similar to what we do with u substitution with just normal integration, how we might have to change the bounds. Again, when we do some examples, you'll see what's going on here, but that's just something to keep in mind. Now, another point I just want to emphasize here is when we're converting from a line integral to a definite integral, we are trying to use c in order to do that. And that's how c is playing a role into this, because if we're just using the arbitrary variables x and y, it doesn't really make a lot of sense, because a line integral is all about trying to integrate with respect to some sort of curve, which we're denoting with a c. Now again, as I've been mentioning, if you do some examples, you're surely going to understand what's going on, and in the next videos we're going to be looking at some of those examples.